We are live, sir.
Okay.
Namaskar, Suaprahan, Kem Cho, Adabars, Wanakam, Shri Krishna, Ram Ram, Radhe Radhe, Sasyakal, Khambagadi. A very good afternoon. मैं अनिल भारद्वाज आप सभी का पीआरएल के 117वें अध्याय में स्वागत करता हूं, अभिनंदन करता हूं। I, Anil Bharadwaj, very warmly welcome you all to PRL's 117th episode. We started the PRL Kamrit Vyakhyan on 4th of August 2021 as a part of celebration of PRL's 75 years of legacy in physics and sciences. And we continue to have this PRL Kamrit Vyakhyan as a series of episodes happening every week at 4 p.m. And this continued for 75 uninterrupted episodes of PRL Kamrit Vyakhyan in January 2023. Subsequently, we started the PRL Kamrit Vyakhyan 2.0 with the sankalp that every month we will have the PRL Kamrit Vyakhyan. And that is what is continuing now. Today, that is 25th of June 2026 at 4 p.m., we have yet another very distinguished Vyakhyankarta with us, Professor Dipankar Bhattacharya, who is head of the physics department, and Professor Sunanda and Santimay Basu, professor at Ashoka University. Professor Sunanda and Santimay Basu, we all know very well, are well-known astronomers and ionospheric physicists who has worked in US, and this community knows them very well, who have been working in this area of upper atmosphere, ionosphere, thermosphere, and space weather areas. Today, Professor Dipankar will be giving the Vyakhyan on superfluid in space, the exotic world of neutron stars. This is a very apt topic and also very exciting topic for all of us to learn more in the area of neutron stars and how we applied basic physics to understand them. We thank Professor Dipankar Bhattacharya for joining us live with us on 117th PRL Kamrit Vyakhyan. And I would now request my colleague, Professor Pallam Raju, to kindly introduce formally Professor Dipankar Bhattacharya to our colleagues who have joined us live on the WebEx panel of PRL, as well as those who have joined live the PRL's YouTube channel. Over to you, Professor Pallam Raju.
Thank you, Professor Bharadwaj. It's indeed my pleasant duty and an honor to introduce today's Vyakhyaan Karta, Professor Dipankar Bhattacharya. As already was told, he's the Sunanda and Santimay Basu Chair Professor in Astrophysics at Ashoka University, Sonipat, where he also heads the Department of Physics. Before taking up this position at Ashoka University, Professor Bhattacharya has served as a faculty at the Raman Research Institute in Bengaluru and also the Inter-University Center for Astronomy and Astrophysics, IUCA, in Pune. He's a member of the International Astronomical Union and a fellow of all the three academies, science academies in the country. Dr. Bhattacharya obtained his bachelor's and master's degree in physics from Jadavpur University, Kolkata, and he earned his PhD degree from IISc, Bengaluru. Then he had few stints as a postdoctoral researcher at the University of Amsterdam and the University of California in Santa Barbara. His work focuses on compact stars, cosmic explosions, and various aspects of space astronomy. And he has been closely associated with India's first astro mission, AstroSat mission, and he chaired several of its working groups. In addition, Dr. Bhattacharya is also a recipient of the M.K. Vainubappu Gold Medal in the Astronomical Society of India, and the C.V. Raman Award for the Space Sciences of the Government of Karnataka. He will be speaking to us on a very interdisciplinary and exotic and exciting topic, which is entitled as Superfluid in Space, the Exotic World of Neutron Stars. With this brief introduction, I welcome and give the podium to Professor Bhattacharya. Professor Bhattacharya, please.
Thank you very much indeed for this generous introduction and for the invitation to talk to this forum. Good afternoon to you all. Let me begin by sharing my presentation. Just give me a second. Is my presentation visible?
Yes, it is visible. Please go ahead.
Yeah. So thank you again for this kind invitation to talk to this very diverse and wide audience. As has already been said, my topic today is superfluid in space, the exotic world of neutron stars. So before we get into the meat of the topic, maybe we should just begin by briefly describing what we mean by a superfluid. So we all know how a fluid flows. Very simply, suppose we have a substrate, a surface, a solid surface, shown in brown here. And let's say there is some fluid flowing in a laminar fashion over this surface. If you have a float on the surface of the fluid, you will see it move along with the fluid flow. And we can ascribe a speed v from above the surface of the motion of that float, and we would say that that's the speed at which the fluid is flowing. But in fact, if we dig deeper into the fluid and then see at what speed different layers of this fluid is moving, then we'll discover something else. You see that deeper you go, closer to the bottom, the slower the fluid flows. And the layer which is just adjacent to the stationary surface is hardly moving at all. And this is what is called a viscous shear. The amount of viscosity of the fluid decides how steep this gradient of velocity is from the bottom to the top. This viscosity causes a friction between layers because they are moving at different speeds, and causes a dissipation of energy and a resistance to the flow. In contrast, if this material happened to be superfluid and we put it in a similar situation and make it flow, then you'll find all layers move simultaneously with the same speed with zero viscosity. Therefore, the flow encounters very little resistance, and there is very little dissipation of energy. So this is one of the special properties of superfluids. There are other interesting properties of superfluids which will come to by and by. So in terrestrial laboratory, superfluidity is realized typically at very low temperatures. And there are just a handful of material which have been seen to exhibit superfluid state. One of them is helium. The common variety of helium, which we call helium-4, at ultra low temperatures exhibit this superfluid property. And this was also the material in which superfluidity was first discovered. When we say ultra low temperatures, let us define temperatures in absolute scale. The zero of the temperature, which is the absolute zero, in Celsius scale is located at minus 273.15 Celsius, which you call 0 Kelvin. The step in Kelvin is the same as step in Celsius. So 1 Kelvin above 0 will be 1 Celsius above this minus 273.15 Celsius. So if you take helium and keep cooling it, get very close to this absolute zero, at temperatures below 4.23 Kelvin, helium-4 becomes liquid. And it has the standard liquid properties as you are used to for any liquid. But if you cool it further, below 2.17 Kelvin, then this strange state of matter appears. Helium-4 becomes superfluid, which was discovered independently in 1937 by Piotr Kapitsa in Moscow and Allen and Misner in Toronto. Helium-4 also has another less commonly occurring isotope, which we call helium-3, slightly lighter than helium-4, but same element nonetheless. So if we cool helium-3, it becomes liquid at a temperature slightly different from that of helium-4, 3.19 Kelvin. But there is no transition to superfluid at temperatures anywhere close to this 2.17 Kelvin. However, if we cool it to very, very low temperatures, very close to absolute zero, below about 0.0025 Kelvin, then it begins to exhibit superfluid property. So this was discovered in 1971. So what causes the difference in this behavior, and what is behind this property of superfluidity after all? So before we get into some discussion of that, let's try to understand what this helium-4 and helium-3 consists of, and how similar are they, and what do they differ in? Helium-4 atom consists of a nucleus which contains 2 protons and 2 neutrons. And there are 2 electrons which then orbit around this nucleus, which then makes up a helium-4 atom. These fundamental particles, protons, neutrons, electrons, each of them carry a property, quantum mechanical property called spin. And this spin is of a magnitude half for each of them. Now, this half is spin angular momentum in units of the Planck's constant divided by 2 pi. So that's the unit of angular momentum. And we will always keep that as our angular momentum unit. And we will look at what is the coefficient multiplying that, which gives us the amount of the spin angular momentum. So each of these particles have spin half. And in a helium atom, the two protons, they have opposite spins, one plus half, one minus half. Two neutrons have opposite spin, one plus half, one minus half. And two electrons have opposite spin, one plus half and one minus half. The total spin of all the fundamental particles that constitute a helium-4 nucleus is 0. In helium-3, on the other hand, everything is similar except in the nucleus, you have only one neutron instead of two neutrons. So therefore, the total spin of this is the unpaired spin of the neutron, which is half. So there's a total of half spin, it's got a total of 0 spin. Using this information, we can now begin to understand the cause of superfluidity, as was already proposed by Fritz London in 1938. The superfluid state, in fact, is caused by a large number of constituent particles. In case of helium-4, it is a helium-4 nuclei, and helium-4 atoms, in fact. The helium-4 atoms condensing into an energy state or a quantum state, which is the same for a very large number of particles. Above the transition temperature, the particles sort of occupy a whole range of energy states. But once it is cooled below the transition temperature, 2.17 Kelvin in case of helium-4, a great fraction of these particles condense and occupy one single macroscopic quantum ground state. And that coherent quantum ground state is the cause of superfluidity. Now, this kind of condensation of fundamental particles can occur if the particles carry either a 0 spin or an integral value of spin. Such particles obey a quantum statistics principle called Bose-Einstein statistics, and these particles are therefore called bosons. And similar condensate can now be realized for other atoms using atomic cooling. Bose-Einstein condensates have been realized in ultra-cold atoms by laser cooling and atomic traps. And superfluid state is a state very much akin to that. Now remember, helium-3 did not have a 0 or integral spin. It had a half integral spin. Particles with half integral spin do not follow the Bose-Einstein statistics, but follow another statistics called Fermi-Dirac statistics, in which particles prevent other particles joining them into any quantum state. So therefore, it is absolutely impossible for fermions to condense and form a condensate like this. So how does helium-3 condense into a superfluid state, albeit at very, very low temperature? So fermions, if they join together and form units of pairs of fermions where spins are either opposite or parallel. So once you have a pair, the total spin of the pair would be either 0 or integral. And if these pair units become the primary constituents of the material, then they can condense into condensate state like this and form superfluid. Fermions can pair into states like this in the presence of any attractive force between them. And this process is called Cooper pairing, and such pairs are called Cooper pairs. And once Cooper pairs are formed, they can then condense and form bosonic condensates. However, at any finite temperature, each of these particles are dancing around because of thermal excitations. So if those thermal excitations are severe, then pairs can break up. So for the Cooper pairs to stay intact, the temperature of the system needs to be lower than the dissociation energy of the Cooper pairs. So that means the transition to superfluid state or any condensate state, therefore, is dictated by the temperature at which Cooper pairs can exist. The transition temperature is therefore decided by the dissociation energy of Cooper pairs, which in case of helium-3 happens to be very, very low. So therefore, one needs to cool helium-3 very close to absolute zero before Cooper pairs can form and then form the bosonic condensate. And similar mechanism actually is behind superconductivity as well, where electrons can pair and form a superconducting state. A superconducting state is again a condensate state where the electrical resistivity goes to zero, and you can have large currents without resistance flowing through the material without generating any heating in the system. Now let's come to the next very interesting property of a superfluid. A superfluid state is a macroscopic bulk quantum state where all particles share the same momentum, same direction of momentum. And hence, a superfluid cannot support bulk rotation. If there is a bulk rotation, then different particles in the superfluid must move in different directions, which is not allowed in a single quantum state. So bulk rotation in a pure superfluid is not possible. So can a superfluid rotate then at all? It can, but to enable rotation, the superfluid needs to then be perforated with vortices. So it is no longer a homogeneous superfluid. And each of these vortices then carry a quantized amount of circulation, which is the Planck's constant divided by 2 pi h cross divided by the mass of the individual condensate bosons. So if you now have very large number of such vortices permeating a certain volume, then the net average angular speed of the superfluid becomes proportional to the areal density of vortices, that number of vortices per unit area. The number of vortices divided by the area times circulation divided by 2 gives you the angular velocity of the overall superfluid. So this core of these vortices do not contain superfluid material. Core of the vortex, material transitions into non-superfluid normal state, and this core dimension is that of the coherence length of the material. We denote this by this symbol psi, and this coherence length of the material is a property of the material itself. Vortices such as this are often called Onsager-Feynman vortices, and they have been experimentally observed. Here is an example, a 1979 experiment where you start with the superfluid and begin to spin up the superfluid. As the spin increases, more and more vortices appear. And they typically appear at the edge of the superfluid and then migrate towards the center. a very, very analogous phenomenon happens in a superconductor as well. A superfluid cannot carry rotation, a superconductor cannot carry a magnetic field. A superconductor, it's a condensate, but this is of charged particles. Magnetic field through a superconductor can therefore either not exist at all, be expelled completely. This is called Meissner effect. Or if it does get carried through the superconducting volume, it is carried in quantized fluxoids. Each fluxoid carrying a quantum of flux given by this. H is the Planck's constant, c is speed of light, q is the charge of the bosonic units which have condensed into the superconducting state. So thus fluxoids occur not in all types of superconductors, but a subclass of superconductors called type 2. The core of these fluxoids have a dimension again of the coherence length psi, and the magnetic field goes through the core and is confined within a screening length. It's called London length lambda. And a type 2 superconductor typically has a lambda which is larger than psi. So you have a full entity of a fluxoid which allows a normal core of coherence length psi and a magnetic field confined within a short distance lambda from the center of the vortex. This too can be experimentally observed. The picture on the right shows such fluxoids, often called them abricosal fluxoids, in a superconducting niobium film, which has been pitted with some prepared holes. And this is then put in a magnetic field, and one can see that these condensation points are where the scanning electron microscope picture. So electrons get trapped by the fluxoids of the superconductor, and therefore you get an enhanced presence of electrons at those locations, which ACM shows. So this is a distribution of flux through the material, and can clearly see that it's full of quantized individual fluxoids. So this is as much as we need to keep in mind regarding properties of superfluids and superconductors before we move to space. So let's now move to space. Start by quickly introducing the evolution of a star which is massive, more than 10 times the mass of the sun, so to speak. In the initial lifetime of the star is kept balanced by the thermal pressure of the gas within the star, which holds it against its own gravity. The thermal pressure is maintained by generating energy in the core through nuclear fusion. The nuclear burning keeps the gas hot, and this hot gas keeps the star from collapsing. However, this core of burning material, initially hydrogen burning to helium, will run out of hydrogen at some point. Once a stage of nuclear burning is exhausted, the core ends up condensing and the envelope ends up expanding. After several stages of nuclear burning, the core will completely run out of all nuclear fuel and rapidly collapse to a neutron star, and the envelope is ejected in a supernova explosion. So now you have a neutron star which has formed. In the formation process, initially one started with almost equal number of protons and neutrons in the material, and then as the condensation proceeded, material became more and more dense, material started getting crushed, and protons started capturing electrons to form neutrons. So the fraction of neutrons began to rise, and the fraction of protons and electrons began to form. In the end, almost 90% of the star has become converted to neutrons, and only about 10% remains in the form of protons and electrons. The density at the center of the star rises well beyond the density encountered inside an atomic nucleus. When protons and neutrons, we will call them nucleons, are pushed to such high density, that means to very short distances between each other, then they begin to repel. The force between two nucleons as a function of distance can be described by this potential curve. If the potential is negative, then the force is attractive. If potential is positive, the force is repulsive. And this transition occurs at a distance of about 1 femtometer, below which the repulsive character of the forces dominate, above which the forces between them are largely attractive. So when these neutrons and protons are pushed to very high density, internucleon spacing becomes smaller than 1 Fermi, and this repulsive force provides the primary support against the self-gravity of this material. You end up with objects with masses of the order of 1 to 3 times the solar mass and a radius of about 10 kilometers. So you can consider the mass of the entire sun condensed within a small radius of about 10 kilometers. So that's what neutron stars are like. Going to a little more detail about its structure, the outer parts of the neutron star at the surface, the material is mostly nuclei and electrons. And as you go inwards, the fraction of neutrons rise. At some point, the number of neutrons becomes so much that they can't be held inside nuclei anymore. So you have nuclei, electrons, and some free neutrons. So that's the inner part of the crust. As you go to even deeper and even higher density, nuclei become unviable. So you just have all neutrons, protons, and electrons all free in this yellow region. At the very core, you have even more exotic material, such as hadrons, heavy mesons, quarks, etc. The exact nature of which is yet to be understood, because we cannot really replicate such conditions in the terrestrial laboratory. So the information has to really come from the study of neutron stars themselves. Now we have free neutrons in this blue region as well as these yellow regions, and free protons in this yellow region. As we have seen in the previous slide, neutrons separated by a certain distance experience strong attractive force. This is the strong nuclear forces. And so do protons. And in presence of these attractive forces, neutrons and protons, which by themselves are fermions, can pair up and form Cooper pairs. And once they form Cooper pairs, they can then form a condensate. And this is what happens inside neutron stars. The neutrons here and here pair up to form superfluid, and the protons, free protons which are available here, pair up to form superconductors. And unlike the terrestrial superfluids and superconductors, where you have to go to low temperatures to realize these states, here, since the attractive interaction is mediated by very strong nuclear forces, the transition temperatures are ridiculously high. The transition temperature of neutrons is about 10 billion Kelvin, and the transition temperature of protons is about 1 billion Kelvin. And the whole of the neutron star is typically at temperatures lower than either. So therefore, the superfluid and superconducting states are easily realized. Neutron stars also possess very strong magnetic field, ranging between 100 million Gauss to about a petagauss. In the superconducting interior, such magnetic fields must be carried via proton abricos of fluxoid, as we have seen in case of terrestrial superconductors. Now, neutron stars also spin very rapidly. The fastest spin we know is about 716 times a second. And most neutron stars we know have spins of the order of a second or so, a few seconds. So the angular momentum of the superfluid part of the neutron star, which is both this yellow and the blue region, must then be carried in the quantized vortices, which we described earlier. In a typical neutron star with a teragauss magnetic field and 1 second spin period, the number of vortices are about 10 to the power of 15 in number, 1 followed by 15 zeros. And the number of fluxoids are about 10 to the power of 31, 1 followed by 31 zeros. The angular speed of the superfluid is proportional to the surface density of vortices, as in terrestrial superfluids, which we have already mentioned. And now, if you have a rotating magnet like a dynamo, it generates a spin down torque. It tends to spin the neutron star down, and it is indeed seen. This is actual measurement of such a neutron star, which we will use as an example. It's a Crab pulsar, and the pulse period is the spin period of the neutron star, and we can keep measuring this pulse period over time. This is a span of about 10,000 days, which is nearly more than 25 years, over which the pulsar is spinning down steadily. Now, in order for the superfluid inside to spin down, this must involve a reduction in the surface density of vortices. That can only happen by vortices migrating outwards. Just as when we spun a superfluid up, vortices migrated from outwards to in. When it spins down, vortices have to migrate from inwards to out. What is not apparent in this particular plot is that this spin down is jerky, with sudden increase in rate of change of spin down, rate of change of spin, followed by slow recoveries. So this is the rate of change of spin plotted over the same time scale, and you can see there are these jumps, then over time it recovers. The jumps are very fast, happens in less than minutes, and then recovery takes many months. Similar discontinuities also are there in the spin period themselves, but their magnitude is so small that they're smaller than the thickness of the line I have drawn here. The discontinuity in spin periods or spin frequency is about 1 part in a billion. The discontinuity in the spin down rate is about 1 part in 1,000. What causes this? And this is thought to be caused by the decoupling and recoupling of the superfluid component with the nuclear crust. So when the superfluid decouples, the crust is facing the external spin down torque alone. the amount of mass coupled is smaller. So therefore, the rate at which the crust is spinning down is faster. And it takes, after a glitch, the superfluid some time to reconnect back to the crust. And then once it is done reconnecting, its spin down rate is back to following the old slope. So that's thought to be the mechanism of these glitches. So these glitches actually encode the superfluid behavior very closely. There are also other long-term and short-term timing behavior. For example, this timing noise, which is also attributed partly to loose coupling between the superfluid and the crust. We will concentrate for the rest of the discussion on glitches. Till date, 727 such glitches have been recorded in about 222 pulsars. And if we now look at the distribution of the size of the glitch, it seems like there are two distinct peaks. So this glitch distribution appears to be distinctly bimodal. Now, why is this so? Is this because there are two different types of neutron stars which are present, or there are two different regimes at which different mechanisms of spin down operate for the superfluid? To address this question slightly differently, we try looking at not a collection of all pulsars, but take one pulsar for which the largest number of glitches have been measured. And this is this pulsar J0537 - 6910, when in one single pulsar, 54 glitches have been observed. And we try looking at the glitch size distribution of the same pulsar. And even in this one pulsar, we end up finding that there is a strong hint of bimodality, which is somewhat surprising, because if there is a process of natural crustal rearrangement and superfluid rearrangement within it, one might expect some kind of a scale-free power law type of behavior, just as earthquakes do. On the other hand, in this case, we see that is not really the case. You seem to have some special scales. So the question we have to ask is, why does, even for a single pulsar, the glitch distribution is bimodal, and what sets the scales? And this is an investigation that we have embarked on over the last couple of years in order to do a little bit more detailed explanation of this. Let us look at the superfluid vorticity in a bit more detail. If we look at the anatomy of a neutron superfluid vortex, we have the vortex core, which is of the diameter of the coherence length, which is about 10 femtometer, around which the superfluid velocity field drops as 1 over the distance from the vortex. In the neutron star, there are, as we said, about 10⁻15 such vortices. When you add up the velocity field of all of these vortices, you have this background velocity field, which is exactly like a rigid body rotation of the whole superfluid. But at the location of each vortex, you have this excess velocity, which corresponds to the velocity field around a single vortex. Now, these vortices, particularly in the crustal superfluid, they can pin to existing nuclei, which means the vortices can overlap with positions of existing nuclei, and then there is a force required to move it away from them. So this is called a pinning force. So that means they are stuck to these nuclear locations. So if the vortices are stuck, then unless they unpin, they are not moving. Now, the electromagnetic torque is acting on the nuclear crust and it is spinning down. So that means this whole vortex array, which is stuck to the crust, is now spinning down. But the superfluid itself has an angular speed which is decided by the density of these vortices and not by the speed of the vortices. So you have the background superfluid, which is spinning at a rate given by the density of these vortices, but the vortices themselves are moving with the crust, which is moving more slowly, which means there's a differential rotation that builds up between the vortex array and the superfluid. The superfluid is passing by the vortex. And in the presence of such differential rotation, the vortices feel an outward push. This is called a Magnus force. The bigger the difference between the angular velocities, the larger is the Magnus force. So the Magnus force builds up as the crust spins down, and at some point, the Magnus force would become strong enough to unpin the vortices. And it's the competition between the pinning force and Magnus force which primarily determine the vortex dynamics. But there are also other interactions, like the mutual interaction between vortices, the boundary effect, dissipation, all of that go into determining the dynamics of the vortices. And it is the dynamics of the vortices which are then responsible for the complex behavior of pulsar spins that we observe. And what we have done over the last couple of years is to create a simulation engine for such vortex dynamics, where we project the motion onto an equatorial plane and look at the dynamics. Here is an animation of one glitch. Vortices that participate in the glitch are shown here, highlighted in yellow. So this is an example of what is happening when a glitch occurs. Vortices move out, dump that angular momentum in the crust, so crust spins up, and at the same time, the superfluid spins down and catches up with the angular velocity of the crust. So this simulation engine can then look at how the superfluid vortex array would behave as a function of time. We can then look at all this glitching behavior, and then for different conditions that we impose, look at whether or not the glitch distribution has bimodality or not. The standard uniform pinning with no external trigger shows some mild hint of bimodality, but it's actually statistically not that significant, and certainly not as strong as what we are seeing in that one observed pulsar. So there must be other effects involved. In order in these simulations to produce really significant amount of bimodality, we would have to impose different pinning strengths in the outer vortices as opposed to the inner part of the vortices, which can happen. For example, if you look at, if this is the rotation axis, the vortices in the inner part have a smaller amount of nuclear material to go through, whereas vortices in the outer part have a larger amount of nuclear material it traverses. And apart from that, the bimodality is mild. We can also look at, over time, how the vortex array changes its distribution. If the pinning is mild, on the left, you can see that absence of vortices, bubbles, move in from the edge and move into the interior. Exactly opposite of what would have happened if you spin and superfluid up. But if the pinning is very strong, the peeling off happens in layers and regions. And this can put a lot of extra stress on the crust and cause the crust to break. So it depends on the strength of the pinning, which we do not have an a priori measurement of. And if the crust breaks and rearranges itself, the pinning distribution may become non-uniform and can create traps, can introduce additional scales, and the crust quake can trigger the occurrence of vortex unpinning. Here we show a situation where we have a set of traps which are distributed across the star, where waffle-like patterns, so it's a non-uniform distribution of pinning sites. And in that, when a glitch occurs, you would see the glitch initiates at one point, and some of these vortices may get stuck into another trap and release vortices from other traps and eventually moving to the full expulsion. What is interesting is that in such a glitch, you would see the glitch rise in a staggered manner rather than smooth rise. So if we in future have enough resolution to resolve the glitch rise, we could tell whether the interior has trapped somehow. But the question is whether in the presence of such traps, scales, and triggers, do we see enough bimodality? So in presence of enough traps, enough triggers, we do see some bimodality, but again, still not as strong as we observe in a real pulsar. What next? Question is, does the bimodality reveal a role of the core superfluid? So far, we have been talking about the crustal part of the superfluid, and we have left out the core superfluid from discussion altogether. And that is because the conventional wisdom is that the core superfluid is very strongly coupled to the crust, because core superfluid vortices are strongly magnetic. As you know, both neutrons and free neutrons and protons are present in the same volume. As neutrons circulate around a superfluid vortex, they will drag along protons as well. If protons are dragged along, they are charged particles, they produce strong magnetic fields. And so each of these core vortices are highly magnetized. Now, electrons, which are present throughout the star, they traverse all the way from crust to the core and back. They can scatter off these vortices and communicate the angular momentum change from the crust to the core superfluids, and core vortices can adjust themselves to keep the core superfluid angular velocity in step with the crustal nuclear material. So in general, core superfluids are not brought into the discussion of glitch dynamics. However, it has been noticed that some large glitches appear to involve core superfluid because the crustal superfluid does not have enough moment of inertia to explain the magnitude of these glitches. Now, if core superfluid vortices do get involved, then there are additional physical processes that will come into being. For example, core superfluid vortices can pin on the proton superconducting fluxoids, which permeate the same volume. And that would introduce an additional scale and possibly cause a bimodality. And this will also couple the evolution of spin and the magnetic field. The effect of this on magnetic field has been explored in some of our previous work, but the effect of this on the glitches themselves has had to wait for development of the techniques that I'm talking about here now. And this is something that we will take up for investigation in our future work. To summarize, neutron stars are the biggest reservoirs of superfluid in the universe. The nature of the superfluid and its properties depend on nuclear forces at high density. So if we can study the superfluid well, we will also infer the property of nuclear forces at high density. The loose coupling between the superfluid and the crust of the neutron star causes it to exhibit a variety of timing phenomena, including, most importantly, glitches. And this glitch dynamics is yet to be understood in detail, in fact, far from being understood. Accumulating observations and advances in vortex dynamic simulations are providing new clues. In fact, just this week, experts in this area are meeting in Portugal to discuss this very subject. And Anantaraman, who is author of most of these simulations that I showed you, is in fact there discussing this in that forum. Thank you very much. I hope you had information that you would find useful.
Thank you, Professor Bhattacharya. This was really wonderful colloquium. So you took us from the mechanism of superfluidity and how one can explain the phenomenon of glitches. So I will be sort of coordinating the question answer session of this colloquium. So
shall I unshare?
You can keep the slides.
Okay,
maybe sometimes people ask questions for a particular slide.
Yeah.
So the platform is open for questions. So anybody who has a question can raise a hand, or they can just type it in the chat box. Then I will read it out. Okay. So by the first, let us maybe by the time I can ask one question, a quick question. Dipankar, my question is related to, you see, in the BCS superconductor, we have 4 known degrees of freedom.
Correct.
And these 4 knowns act as a pairing glue for the electrons.
Correct.
So in metals, the electrons Fermi energy is in electron volt.
Yeah.
And the phonon energies are in milli electron volt. So there is order of magnitude smaller dynamics with the pairing interaction.
Yeah.
But in the case of superfluid, so there is a Fermi energy because these are fermions, the neutrons and protons are fermions. But then you have a nuclear forces which are acting as a glue.
Correct.
So is there a hierarchy similar to what exists in metals? Do you have that hierarchy in this case?
Yeah,
also?
but you don't need phonons in this case because
for sure there is no lattice there.
Already attractive.
Yes.
And that energy scale is in GeV. So that is the reason why the transition temperatures are also in GeV.
Yeah. So basically, the point is that in case of BCS superconductors, the pairing dynamics has to be much smaller as compared to the dynamics of the Fermi energy. So I think that is met, I guess.
That here also it is met. So
yes.
Fermi energies are high. So
I understand. Okay. Okay. So there is a question from Varish. Varish, can you unmute yourself? Varish?
Yes. Can you hear me?
Go ahead.
Yeah. Thank you, Professor Dipankar Bhattacharya. Very nice talk. So my question is about this bimodality of the glitch. Is it a kind of a observed thing that in the glitches you can see the bimodality?
Yeah, that is because that's where it started. Both these are observed. These are plots constructed from observations. This is a distribution of glitch sizes over all the pulsars. This is a little old, 2022, so 178 pulsars, 543 glitches. And this is in just one pulsar, 54 glitches. In both cases, we see the bimodality.
Yes, but is it a kind of a common phenomena, or is just like a seen in some of the cases?
I'm not sure what you mean by in some of the pulsars. Or,
yeah, only some of the pulsars.
The problem is that we cannot do this for all the pulsars.
Okay.
For most pulsars, we have only 2, 3, 4 glitches. So we cannot do a distribution. So this is the only pulsar for which we have large number of glitches, and we can do this distribution significantly. And otherwise, we have to go to the total population, which is this, which is a sum of all the pulsars.
Okay, and from this the pinning, you're saying that pinning of the crust with the superfluid. So is it explained? You're trying to explain that in some cases, depending on the parameter, how do you take? Then in some cases you can see that there is a bimodality, and in some cases you do not see.
Oh, yeah. So at the moment, what we don't know is what the pinning forces are, how they are distributed. These are all quantities which are not known a priori. So we are trying to see, starting from basic principles, what ingredients we need to include in the simulation so that we can create bimodality. And
Okay.
a two level of pinning, that is a spatially separated zone of different spinning strength, is one way of creating bimodality. That gives you this one, right? Whereas how realistic that is something that we still have to really figure out, because these are all sort of toy models.
Thank you.
I think Sachi has a question.
Yeah, so hello Dipankar. This is very nice, it's a nice talk here with this neutron stars. Am I audible?
Yes, you are audible.
Yeah, you're audible.
So basically, the cause of glitches is because of coupling between the crust and the superfluid near the core, right? So does it depend on the spin period of the neutron star, the
Yeah.
strength of coupling?
Strength of coupling, I don't think so, but the rate of glitches, of course, does depend on the spin period. So the slower it is spinning, the fewer the glitches, the glitching rate is lower.
Yeah, is there any information regarding the slowest pulsar where glitches are seen?
Of course, I mean, of these 222 pulsars, there is a whole range of spin periods. But I don't know what exactly you mean by what information. But yes,
Because I believe all those are radio pulsars, right?
they're all radio pulsars.
So it's difficult because it's difficult to detect in X-rays in millisecond pulsars. Even the glitches are there, but we don't detect because of measurements.
So for millisecond pulsars, I think only rare have been seen. But
So, because of detection.
yeah.
So, yeah. Okay. Yeah. Okay. Okay.
So there is a question raised hand by Churchill Divedi. So could you please unmute yourself and ask the question, Churchill?
Yeah. Hello, sir. Thank you so much for the talk. I just wanted to know, like, from pulsar timing perspectives, is there a way where we can get more insights into measurement of these glitches? For example, if we get an estimate of the bending delays or aberration delays for these pulsars, can we do something to complement this research?
I mean, the glitch research is intimately connected to pulsar timing. And all this actually comes from the reservoir of pulsar timing measurements. So I think whatever the timing measurements can do are already being done. But of course, a more sustained high cadence timing of a large number of pulsars is something that is still to be done. So that's an area which is important to pursue in order to advance this field.
Dipankar, so there is a weak Sarkar. So before that, I want to ask one question. You see, so there is a Landau critical velocities. If the Landau critical, if some object is moving through a superfluid, it's Landau. If the velocity of the object is greater than the Landau critical velocity, then it creates excitations.
Yeah.
Basically, and then the thing is that now in this superfluid in a neutron star, the neutron star is spinning, right?
Yeah.
So is it possible, or are there observations where the spinning speed of the neutron star is so large that it populates whole of the superfluid with so many vortices that end of the day
The superfluid can
it's a
get
superfluid.
destroyed.
It kills the superfluid.
Yeah, it won't happen even in the fastest neutron star.
So it won't happen. Superfluid is always there.
It is always there. Yeah.
Okay. Thank you. Yeah. Avik, you can unmute yourself. Hello, Avik. Avik Sarkar?
Can you hear me?
Yes, you can hear.
Yeah, now we can hear.
Okay, okay. So what I am trying to understand is that I'm trying to understand the system itself. How do you simulate the whole these are MCMCs, Monte Carlo simulation,
No,
or
no, no. These are not Monte Carlo simulations. These are dynamical simulations. So we have a set of dynamical equations,
Mhm.
which
So what are
we
these equations? Basically, these are
okay. So
hydrodynamic equations. Yeah.
yeah. So no, I did not show you the equations because I thought maybe too
I
much.
was afraid that I missed it. Okay, no.
No,
So
no, I did not show the equations, but I can show you. It's just give me a moment. So these are the equations which we use basically.
okay.
So this is this
So nu is a collision,
no,
is
this
it?
V. These are superfluid
Okay,
vortex
a
velocity.
velocity of okay.
These are
So
vortex
in
velocities.
2D on 2D plane, you
On
try
2D
to
plane,
simulate.
it is
Yeah.
the forces are integrated along the length of the vortex and projected onto a 2D plane.
And how they move, that depends. That is a random force, right?
It's
How
not a
they
random
move.
force. Force is not random. We don't
Okay.
have a stochastic component added to this at all. That may be present, but we have not done that. This is
Okay.
all deterministic component, and that
Okay.
has to do with the relative velocity of the superfluid and the vortex. And the relative
Okay.
velocity is because vortex is pinned. So this
Ah,
pinning potential keeps the vortex in place, but
okay.
the this these two give you the average superfluid velocity. So this now gives you a differential velocity, and that gives you a Magnus force, and that gives a force, which then counteracts the pinning force, and eventually they can unpin themselves.
So you solve it in the Cartesian and then convert it
Yes,
to the polar.
solve it in Cartesian coordinates.
Okay, thank you.
Santosh, yeah, please go ahead.
So, Dipankar,
Hi.
nice overview of the glitches. I wanted to ask from observational point of view, what would be a more appropriate way of observing more glitches? Would it be like one very sensitive big detector, like what we are talking for few meters square, and then keep observing the fainter neutron star, or maybe because this timing wise it's simple, so we can have multiple smaller instruments which are simultaneously observing more sample of pulsar. So which would be more beneficial? And then also in terms of final understanding of the nature of the matter at the neutron star core, which is where we know that our radius constraint is more important. So from both these points, whether the more pulsar monitoring simultaneously is appropriate, or whether a single large instrument observing huge number of pulsars but with a more deeper sensitivity of measurements, that would be more useful.
Okay, so what the strategy that people have been following is that there are a few pulsars which people have decided to just follow continuously almost. Trap pulsar, Villa pulsar, and a couple of other pulsars. They are followed at the highest possible cadence using some dedicated telescopes. For example, the Jodrell Bank Observatory observes the crab pulsar. It keeps following it. Then there is a observatory in Tasmania in Australia, which keeps observing the Vela pulsar. But there are only 2 or 3 such pulsars which are continuously monitored. The other pulsars are sort of kind of hit and miss. So there are a bunch of pulsars which will be observed for some time and then move over to other pulsars and so on. And this is basically just the availability of telescope time to spend on these objects. So I think both are important in the sense finding larger number of glitches in individual pulsars is as important as enlarging the number of objects in which glitches have been found. So I think at the moment the observations here are really not very much. The 700 odd glitches distributed across 200 odd pulsars actually is fairly sparse number. So increasing it in any dimension is useful.
Yeah. But so, I mean, does it mean that having a smaller number of more telescopes would be useful, particularly for this timing monitoring? Because these are, I mean, if you are looking for radio telescopes, then maybe you are a simpler, relatively smaller antennas, because these are supposed to be a strong radio sources. I mean, so in that mode, whether large array distributed over multiple, let's say, education institutes or something like that, whether that kind of campaign would be more useful?
It is certainly possible. One will have to caution, however, that many of these pulsars are faint. So in order to be able to catch glitches with high cadence, you need to be able to practically see single pulses. If not single pulses, integration over not more than a few pulses. And that is not easy even with a reasonable sized radio telescope for really faint pulsars. So the sizing of the instrument has to be appropriate for the level to which you have to go. But there is certainly a big space there which one can fill.
Thank you.
So any other question from the WebEx panel? Yeah. So meantime, actually, there is Dipankar. There is one question in the YouTube. So
okay,
a couple of them, but I think we can take one if the time is okay. The time permits. Okay. So there is one question from Srihar B. So Srihari B. So he writes, could the glitches and merger signals from superfluid neutron star reveal how quantum mechanics and general relativity finally unite in extreme gravity?
It is true, but I think as far as the observations go, disentangling effects like that is still quite far away from reality. But yes, what we are seeing is a combination of all of this.
Yes. Okay, so any other questions from any colleague? If not, then so I would like to request my colleague Durga Prasad.
Hello. Thank you, Professor Navinder. So we have come to the end of today's Vyakhyaan. So it's my pleasant duty to deliver the vote of thanks. So on behalf of the Director PRL, PRL Amrut Vyakhyaan Committee, and the entire PRL family, I thank Professor Dipankar Bhattacharya for accepting our invitation and delivering our 117th Vyakhyaan of our PRL Amrut Vyakhyaan series. Thank you very much, sir, for accepting our invitation and providing a very interesting Vyakhyaan on a intriguing topic, superfluid in space, the exotic world of neutron stars, wherein you have detailed about the neutron stars, their structure, and how the interior superfluid drive their various processes, particularly their rotation. Also, many thanks for patiently answering all the questions from our viewers, both from YouTube, also WebEx panel. Next, I thank our Director, Professor Anil Bharadwaj, for his constant encouragement and continued support for keeping this series of Vyakhyaan going on so well, even after 100th episode. I thank our Dean, Professor Palam Raju, Professor Nandita, Chair, and Dr. Lokesh, Co-Chair, and all the members of PRL Amrut Vyakhyaan Committee and all others behind for their continued efforts. Most importantly, a lot of thanks to all our participants who have joined today, both on YouTube and WebEx panel, and participated in the discussions. With this, we come to the end of this episode of PRL Amrut Vyakhyaan. It's now time to sign off from PRL. However, please do join us for our next episode of another interesting Vyakhyaan. Till then, stay tuned and keep following PRL updates on its website and social media platform. Thank you very much.